If you recall, this week we've been talking about operations with vectors. There was vector addition and scalar multiplication, the two that we need to do linear combinations of vectors. And then we have two kinds of vector multiplications where we're multiplying two vectors. The first was the dot product, which is a scalar product. A vector dot another vector will produce a scalar. The way we want to think about the dot product is that this is multiplication at an angle. This is multiplication at an angle. So all we're doing is finding the product of the magnitudes. That's what we got here. U times V. That's just the product of the magnitudes. But then we reduce the product because we're at an angle. We're not using all of one vector in the direction of the other vector. The fraction that we get is the cosine of the angle in between them. So this is multiplication, but at an angle. So a way to think of the dot product is as multiplication at an angle. Notice that the dot product is just going, if the vectors u and v are going in the same direction, all we're doing is multiplying their magnitudes. So the dot product is a product of the magnitudes, but it is nerfed by the angle. So if two people are pulling something and they're pulling on the same rope, all of their magnitudes are pulling in one direction. But if one person is pulling at an angle to the other person, then we're not going to get the product of both of those magnitudes. Oops. So think of it as a multiplication, but at an angle. Remember the angle, the cosine of theta, cosine of 0 is equal to 1. So if the vectors are going in the same direction, then the dot product is just the product of the magnitudes. That's the best place to start. So if the vectors are going in the same direction, dot product is just the product of the magnitudes. If the vectors are going in the same direction, the dot product is the product of the magnitudes. If the vectors are at an angle, let's use an acute angle, that's going to reduce the effectiveness of one of those factors. So if theta is more than 0 but less than 90, if we have an acute angle, then the cosine of theta will be between 0 and 1. So if the vectors are moving at angles, that reduces the product. But the product is reduced because the cosine will be a number between 0 and 1. Moreover, as theta starts off at 1, when theta starts off at 0, cosine of theta is 1. And then as theta increases up to 90, cosine of theta decreases down to 0. When theta equals 90, I just have one. I don't need to write the whole range. When we get to cosine of 90, cosine of 90 is equal to 0. And so that's like the vectors not helping each other at all. It's like the vectors aren't working together at all. This is a great way to determine if vectors are perpendicular. This is a good way to find a vector perpendicular to a given vector. Find a vector where the dot product is equal to 0. When we get past 90, cosine drops negative. So for theta between 90 and 180, cosine of theta will be between -1 and 0. So now the vectors are kind of going in different directions. They're working against each other. If there's an obtuse angle between the vectors, it's like they're working against each other. If the vectors are at an obtuse angle, it's like the vectors are working against each other, at least partially, because there's still an angle. And then when theta drops down all the way to 180, then cosine of theta is -1. And so the vectors are working in opposite directions. Yeah. Correct. Because if we think about the starting place, if the vectors are going in the same direction, then the dot product is just the product of the magnitudes. As soon as there's an angle, it's like we could think of it as the default thinking for vectors is thinking in terms of work. Like two people pulling in the same direction, you're just going to multiply the magnitudes. You're just going to multiply their force. But as soon as one of those vectors is at a bit of an angle, that reduces the cooperation because one of the vectors is pulling off at a funky angle. And so only part of their force is being applied in the direction with the other vector. That proportion is the cosine of theta. This is the same thing that we do when we break a vector into horizontal and vertical components. So if we have a vector with a magnitude, well, I've been calling them forces, so let's make it a force. If I have some force going at an angle of theta, only part of that force is going along the horizontal. The fraction of the force that we get applied to the horizontal is the cosine of the angle we are from the horizontal. Usually when we're making this calculation, all we care is the scalar amount, because when we say horizontal, we have included direction information. But in the case of vectors, the actual vector FH would be the magnitude of F times the cosine of theta in the direction of the I vector. So most of the time, since we're saying horizontal component, we don't need to remind ourselves of a vector. We can think of that since horizontal is where we're including the direction information. We don't need to say anything more. We just need the scalar, the amount that's going horizontally, because we've said horizontally. What we want to do with the dot product, so this is a dot product calculation. What we want to do with the dot product now is to generalize this. And instead of saying how much of this vector is going horizontally, what is the horizontal component of this vector, we can look at a vector u and a vector v and say, what is the v component of the vector u? So essentially take this problem, and instead of having this vector I, do this at some other angle, where I is some other vector. How do I break a vector into components where one is parallel to another given vector and one is perpendicular to that given vector? So what we could think of that we're doing with the dot product is we're trying to generalize horizontal and vertical components. Instead of horizontal component and vertical component, I have a vector u. What's the component of that vector parallel to v, some other weirdo vector? And what's that component perpendicular to v? I'm not going to make them work out nice. Just let them, the square root, irrational numbers are numbers too. I don't know why I'm having issues. Let's say u is 1i plus 2j. I do want something I can draw. And v is the vector 3i plus 4j. At least one of them will have a nice magnitude. I need more separation. I thought I was going to get more separation. Oh, it's because I went 3/4 and not 4/3 and not 3/4. Crank this out to 6. So here we have these two vectors. The idea here is that instead of just using I and J all the time, where everything is horizontal and vertical, we're going to think more in terms of, I put the V in the wrong place. We're going to think more in terms of our linear algebra. And we're going to say, you know, U and V are non-collinear vectors. This is a perfectly valid basis for two-dimensional space. So notice that U and V are not pulling in the same direction. There's some acute angle between them. So I can't just find the product of these two vectors. I'm going to multiply these two quantities. I'm not just going to take all of magnitude of U and all of magnitude of V. Magnitude of U is less effective because it's at some funky angle. It's kind of pulling us off course. So we're going to imagine instead of I, we're going to imagine this vector, a unit vector in the V direction. So here's the vector V, and here's a line of the V direction. And I think, how much of U is going in the V direction? What is a component of U running parallel to V? Instead of taking U and dropping it all the way down to horizontal and saying it's 1I plus 6J, for whatever reason, I and J are not going to work for our particular problem. I care about this vector. What is U in relation to this vector? That's bad grammar. What are U in relation to this vector V? So instead of using the unit vector I and the unit vector J, I'm going to make a new unit vector in the direction of V. This is a replacement for the vector I. I'm not going to just use the standard I and J for my unit vectors. I'm going to make a different unit vector that's going in the direction of V, but I want it to be a unit vector because I want that just to contain the direction. We're just trying to be different. We're not using I and J like all those Brittany and Justin wannabes. I don't have enough hair to flip like the goth kids in South Park. So think of this unit vector in the direction of V as a replacement for that boring ass I and J. I don't know why I got to be disparaging against I and J. I and J, you are perfectly acceptable. You are our favorite unit vectors by far. This is just for demonstration purposes. Now that I'm looking at the I, it looks like it's flipping me off. It's like, oh, you don't like horizontal and vertical? Well, I. So think of it this as an I replacement. Because for some reason, our shit's got to be at an angle at this point. So how much of U is going in that direction? That unit vector that we're using to replace, I'm just going to take V and divide by the magnitude of V. I'm going to take its magnitude of 5, and I'm going to chop it down to a magnitude of 1. Just divide by the magnitude. That's the magnitude of V. I know it's super basic, just use a 3, 4, 5 triangle, but I mean, what am I gonna do? Draw 5, 12, 13? I go 5, and then I go 5, and then I go, oh, now I gotta do 12. And then given the paper, I would have gone like 5 and then like 12, but then it would have been like 13. And it's like, so what we're finding is now instead of projecting u all the way down to the horizontal and seeing what multiple of I is this, we're projecting u down to the vector v. And that will be a component of u in the direction or parallel to the vector v. Now, I don't want to multiply by the two magnitudes. I've taken the magnitude out of v. So I just want u dot this unit vector in the direction of v. Otherwise, things are getting distorted. So I'm going to take u and find the dot product with this unit vector. So if I find the dot product of u and 3/5 I and 4/5 j, I combine the two steps. My mission to make people skip steps is like starting to infect my mind. So I'm going to take u and find the dot product, not just of v. I just want to know how much of u is going in the v direction. So I just need to describe the v direction. And I wrote it upside down. All right, I don't know if this is a more coffee problem or a less coffee problem, but I know what solution I'm going to be applying. I don't want just the u dot v. I just want the direction of v. That's why we use unit vectors. That's why I is a unit vector with a magnitude of 1. So I'll take the 1, 6 and find the dot product with not 3, 4, but with 3/5 and 4/5. So I'll have 3/5 plus 24/5 or 27/5. Now, if we look at our diagram, we can see that 27/5 is a little bit longer than our original v. 27/5, our v is 5, 27/5 is 5 2/5. And that's what we got. That's that little extra 2/5 at the end. And there we see it. There's a little bit more than the magnitude of v. The dot product of u and v is going to take this quantity and multiply by the magnitude of v. And it'll be less than just all the magnitude of u times all the magnitude of v. Dot product is a scalar product, and it's working at an angle. Looking ahead, this is important because remember, integration is just multiplication, but one of the factors is continuously variable. That's the thing about integration. Integration is the primary way we study integration is the area under a curve. And the way we calculate the integral, the way we set the integral up is just take length, which is the continuously variable length, multiplied by these ever decreasing width. Length times width. It's a multiplication, but one of the factors is continuously variable. So that should, since the dot product is a multiplication, we're going to be doing the same thing. We're going to have some surface and a bunch of vectors are going to be going through that surface, but I'm not just going to multiply the vector going through the surface times a vector describing the surface, because they're going to be going at funky angles. So the product that we're going to need, if we need a scalar product, the product we're going to need is the dot product because it's working at a funky angle. This is how we multiply when our factors are at angles. The dot product is how we multiply when our factors are at angles. Does that make sense? No, it doesn't. You don't get to agree right away. It doesn't make sense. It has to be a little bit weird. If it's a little bit weird, if you're like, oh, the F are you talking about, Leach? I'm like, oh, good. That is the correct answer. That's why this class is not 3 minutes long. That's why this class is 17 weeks long. Because I have to be able to say that, and then a couple days later, say it again. Then a couple days later, say it again. And then a couple days later, say it again. Wait a couple months, say it again. And you're like, oh, something makes more sense when you talk about it now. And you'll say fun things like, why didn't you just say that in the first place? Because the first place was a month ago, and we needed that month for it to just sit in the back of your mind. Do you know what I mean? It's kind of like trust the process. Yes. Yes, that is one example of how it functions. Electric flux. So that is one of the things we'll do, because we'll describe the electric field, we'll describe an electric field as a bunch of vectors. Another way we can think about it, okay, I'm not a dad, but if that's too shocking for you, I'm not a dad, but imagine like imagine the vector field of the airflow in this room. At every point, we can imagine a vector. And those vectors are changing continuously, right? There's no point where the air is immediately going in a different direction. It's got to kind of flow, kind of like temperature. Imagine temperature. Temperature has to be a continuous function. That's the way we define the concept. But think of the airflow in this room, right? And now, imagine that air flowing through some surface. Imagine that air flowing through some surface. And that surface is some funky shape. Now, if we simplify the problem and say all of the air goes one direction and all the surface, and it's going perpendicular to the surface. So for those of you not at home, I'm doing this. Air flows perpendicular to the surface. What we're using to describe the surface, because cross product is coming up probably tomorrow. What we're using to describe the surface is not all these vectors on the surface. We're describing this surface with a normal vector. So if the air is flowing perpendicular to the surface, then all we have to do is multiply. Magnitude of the air times the magnitude of the surface. That would be like how much the surface captures the air or something. I don't know. It's physics and engineering. I don't know that shit. I'm the fucking math guy. What do you expect me to know about like airflow and shit like that? I passed thermodynamics according to my transcripts. Like, but if you gave me like a thermodynamics test now, I'd be like, oh, what is wrong with you? That happened in like 1990. No, 1991. Okay, I'll be honest. It happened in 1991 and 1992. I took thermo twice. I bailed on it the first time. I didn't flunk it. I'm like, oh, you're not going to flunk me, and I hit the ejector seat. What grade you get in thermo this semester? W. Why'd you quit? Hard to pass when you don't go to class. But anyway, that's all beside the point. We're describing this surface with a normal vector. And if the air is coming at the surface perpendicular, all we got to do is multiply, because the angle between how we're describing the surface normal and the airflow through the surface, they're going in the same direction. The angle is at 0 degrees. Dot product is product of the magnitude. But if the air is coming at an angle to the surface, not all of the vector of the airflow is perpendicular to the surface. How much is perpendicular to the surface? That we calculate with the dot product. So instead of just multiplying airflow times surface, which turns into an area, instead of just multiplying airflow times the surface, we find the dot product of the airflow and the surface. It becomes an integration problem when the airflow starts being like, oh, I'm going to be different at every point, but I'm going to change continuously. And you're like, oh, son of a bitch. We have to do the integration thing again. I can't just multiply because it's not constant. One or more of our factors is continuously variable. Now we've got to integrate. This is the big picture in calculus. Now I have to know every time I'm talking about an application of vector field flowing through a surface, I have to steal that application from somewhere else and make it and some people think, oh, it's to make it relevant to the engineers. It's like, it's not like you're going to be making this calculation later on when you're an engineer. Things are going to be changing too much. Computers are going to be doing that shit for you. What? And when you don't have a code handy, it's like, well, hey, what's the code for this particular calculation? Well, I don't know. That's kind of new. It's like, oh, well, let's hire someone. Then you're going to hire a computer programmer who's probably going to hire a mathematician to consult. But this is how we want to think about dot product. How we calculate dot products, whatever. How we think about dot product is multiplication at an angle. If everything's going in the same direction, cosine of theta is 1. We just get the magnitudes. Wonder twin powers activate, right? Magnitude of u multiplied by magnitude of v. But if our two vectors are at an angle, it's not going to be all the magnitude of u times all the magnitude of v. Good news is that the fraction is well known. It's just the cosine of the angle between our two vectors. Any questions? It sounds like I've been saying the same thing kind of a bunch of different ways for the last 2 days. That's because I've been saying the same thing a bunch of different ways for the last 2 days. It only continues on for the next 17 weeks. So, but remember, you don't get songs stuck in your head because you hear them once. You get a song stuck in your head because you hear it every day. If our calculations are correct, every day for 17 weeks. Because we have a 17-week semester. If we were on the quarter system, it would be every day for 11. Quarter system. And some schools run 15-week semesters. Any questions? Oh. I think one of the tricky things when it comes down to learning math, one of the tricky things that comes down to learning math is kind of encased in the idea of a limit. Like every once in a while I've been asked in the past, like when did it click for you? When, like, someone will ask me, when did calculus click for you? Sometime in the past 33 years. When I started calculus in 1989. That's when my first calculus class was in 1989. Long, long time ago, when dinosaurs roamed the earth. And I think one of the things that really throws us off about learning math is that we're waiting for some moment where everything clicks into place. And that's just not how it works. It is a continuous grind. It's not just like everything is flat and then all of a sudden we get it. It's not binary. It's not a switch like that. Stuff makes more sense over time. The more you think about it, the more it makes sense over time. The only reason that I have this picture in my head, I have this solid picture of calculus, or mostly solid picture of calculus in my head, is because I've been looking at calculus and thinking about calculus, and most importantly, talking about calculus to other people for the last 30 years, fairly consistently. It was only spotty at the beginning, because I was only intermittently talking about calculus, and it wasn't until like 1992 that I really had to start talking to calculus to people on a regular basis, because I started working as a tutor. And then my only actual job has been essentially this one. So for when I was in grad school, what was my job? Talking to people about math. Now that once I graduated, what was my job? Talking to people about math. And I've consistently had a calculus class for the last 23 years. And that's why it makes sense to me. Now, whether I can take that information in my head and make it make sense to you, I mean, that I'm still working on. That is a skill that I'm still trying to figure out. I'm wondering if it'll finally make sense, like after I retire, or maybe like I'll on my deathbed. It's like, I see it now. So I don't know. But I think one of the misconceptions that we get is that we're waiting for some kind of, I think they call it an aha moment. It's like, oh, eureka, everything clicked. And for the most part, shit don't work that way. You just continuously, gradually know and understand more. And the only way to make that happen is to continuously and gradually try to understand more. Don't wait for it to click. Don't wait for some magical moment, some magical instant. Put in the time. That's it. Put in the time. I have a friend that says, she says, I don't have the math gene. And it's fine. She's not a student anymore. She's actually retired now, so it's cool. She can dislike math all she wants. She can not want to learn math. At a certain point in your life, you don't have to learn anything anymore. If you get to that point, then it's kind of like you win. It's like, I can coast until I die. The important part is when you reach that point, just shut the fuck up. Once you get to the point where you don't need to learn, you don't feel like you need to learn anything anymore, then just shut up, because you're going to be an utter pain in the ass for the rest of us who are trying to like do something better. You're going to hold us back. Just go along and silently look down on all these people trying to do better by the human race. Right? Look, just shut up. But it's not like that. Math is going to be differently hard for different people. But there is nothing physically stopping you from being able to learn math. There's nothing that's going to physically stop you from doing this, because learning math, this activity of learning math, wants one thing from you: your time. It's a function of time. That's it. It's a weird function of time, because some of you in this class, the time is like close to zero. Your friends are not even going to notice how much time it takes. And you're like, oh, I totally understand it. And then they're like when they explain it to me, I'm like, oh, yes, you get it. Then when they explain it to you, you're like, oh, what the F are you talking about? Which means that they don't really get it, because they can't communicate it yet, right? And for you to get to that point is going to be more time. And that's it. And the only reason for that is that they're not you, and you aren't them. They're different. Does that make sense? Some people are going to just have a longer amount of time. There's an amount of time that you need to spend thinking and doing these things. And it's a lot for some people. And it's a small amount for other people. And for some people, spending whatever amount of time, spending 1 hour doing math is okay. If I can accept spending an hour doing math. And for some people, spending an hour doing math is fucking torture. We react to things differently. Some people go to a Taylor Swift concert and lose their fucking mind because they're so happy. I would be at a Taylor Swift concert and I would be like, the happiness that I would get was from watching other people be happy. Because I'm like, I don't find the music offensive, but I also don't find the music super engaging. I'd also be super stressed out because I'm in a room full of people and fuck that. But for some people, spending an hour doing math is perfectly acceptable. For some people, it will be super fun. For other people, it would be absolute torture. But it's just an amount of time and how well psychologically we can cope with spending that time. Does that make sense? But I promise you, there is nothing physically stopping you from understanding math, from learning and understanding math. It's just a matter of time. No question? Comment? I know on a certain level, if you're here at this point in your mathematical career, you're in Calc 3. At a certain point, I know you kind of inherently understand that. You just inherently understand that because that's how you got here at your young age, right? So when you encounter other people, they have a different experience than you. You can tell they have a different experience than you because they ain't you. So when people are struggling, have some sympathy. Question? That's fine. You know, the basic substitute in trig substitution, it's one of my favorites. So trig substitution is like one of my favorites because the basic substitution is the point. Getting from your x integral to your theta integral, that's kind of the point. Getting from your theta integral to your theta antiderivative, that's kind of beside the point. That's really the shitty part. You know what I mean? Now, if you don't know what I'm talking about in trigonometric substitution, where you have your x integral, your theta integral, your theta antiderivative, your x antiderivative, if that's not the picture you have in your mind of trig substitution, your Calc 2 teacher did you dirty. If you were in my class, it's just because you don't remember and it's your fault. I'm just kidding. That means I didn't do a good job. All right, that's it for today. Dot product, multiplication out of angle. That's it for today. I'll see you all on tomorrow. Everybody have a good day. And thanks for playing. No, I didn't have a sign-in sheet.